Last time we started section 9.1 and we were taking a look at sequences. We had done one example where we found several terms, first 5 terms of a particular sequence by evaluating 1 through 5 for the value n. And what we're going to talk about now is how we figure out what happens sort of long term. When does a sequence have a limit? If it has one, how do I find it? Those kinds of questions. So to start with, sorry, where I put it. Okay, to start with, sorry about that, we're going to just define what it means to talk about a limit in terms of sequences. Because you've done limits before, they were in terms of functions, but what you will want to remember that we talked about last time was that sequences are actually functions whose domain are the whole numbers, the natural numbers actually. So we'll start with a definition by way of reminder. That's pretty good size. Let L be a real number the limit of the sequence a sub n is L written in familiar limit notation, the limit as n goes to infinity of a sub n equals L if, now you're going to feel like you're in Calc 1 again, for every epsilon greater than 0, there exists, that E backwards, if you'll remember, means there exists a capital M greater than 0 such that if the absolute value of a sub n minus L, not if, that the absolute value of a sub n minus L is less than epsilon, whenever n is greater than capital M. If the limit L of a sequence converges, exists, that was the next word, exists, then the sequence converges to L. If the limit of a sequence does not exist, then the sequence diverges. Okay, so we're going to take a look at a few limit properties. These will not seem foreign at all. You've seen these before, just not as they specifically are written as to relate to sequences, but these are limit properties. Limits have the kinds of properties that you would kind of hope and expect them to have. So let the limit as n goes to infinity of a sub n equal to L, and the limit as n goes to infinity of b sub n equal k. So the first one then is if you have the limit as n goes to infinity of a sub n plus or minus b sub n, what would you hope and pray, so to speak, would be true about the result? It's L plus or minus K, right? A second one, limit as n goes to infinity of c is just a constant, I'll write that down just a minute ago, in a minute afterwards, c times a sub n, so a constant times a sub n. What would you think that that one's limit would be? CL, right. Okay, and I'll write it here, this is c is a real number. That's not a hashtag, by the way, that's a number sign. I know you guys might not realize that, but just to clarify. All right, third one. If you have the limit as n goes to infinity of a sub n times b sub n, what would you expect that one to be? Yeah, L times K. Or you can just write LK if you prefer. The last one of these particular properties would address what operation? Which one have I not done? Division. So if you have a sub n over b sub n, what would you expect it to be? L over k. However, division always has the possibility that what could happen if we were just not being careful potentially. You could have something with a denominator 0, so obviously this is not going to exist if b sub n is equal to 0, so b sub n is not 0, and also k can't be 0 for this to make sense, okay? Aside from notation, these are the exact same limits that you have, limit properties that you saw in Calc 1 as they related to functions. And that kind of makes sense because we already said that sequences really are just a specific type of function with a specific type of domain. So we're going to do an example of limits. We're going to determine if the sequence converges or diverges and if it converges, find the limit. So this is actually our second example because we did the sequences example last time. Our sequence for this one, a sub n, is 3n cubed minus 1 over 2n cubed plus n. All right, so we are going to do something. Again, this is not the first time you've seen what I'm about to do. We're going to find a limit. One of the ways that we talk about finding these limits is by looking at the fact that we've got a polynomial on the numerator and a polynomial in the denominator on this one, right? And polynomials are kind of nice to work with. We're actually going to take these and we're going to notice that on this one, the highest degree exponent is a 3, right? So what we're going to do is we're going to multiply the numerator and the denominator by 1 over n cubed. Now, it happens to be that both the numerator and the denominator have n cubed in them. That's just happenstance. This process still works even if you have an n cubed on top, but it's only an n squared on bottom. Okay, you can still do this. You're going to use whatever your highest degreed exponent is to multiply by that ratio. All right, so let's see what happens when we do that. So if I take this particular one, on the numerator here, that's going to give me 3, and then minus 1 over n cubed. So far, so good. And in the denominator, it's going to give me 2 plus what? 1 over n squared. So first, kind of like to develop for you what we're doing and why as a reminder. The reality is that if you were to look at these equations in your calculator as a function, they would be a rational function that's going to be tapering down to the x-axis, right? They're leveling off at the x-axis. The x-axis has a y value of 0. So over time, 1 over n cubed and 1 over n squared, their limit is 0. Does that make sense? Yeah. So this is our goal. Our goal is to get most of this stuff to go to 0, to disappear. Now, logistically, like how do I write this down? Well, we write it down with limit notation. So our limit, as n goes to infinity, of 3n cubed minus 1 over 2n squared plus 1. And I'm going to have 1 over n cubed here. This equals the limit, as n goes to infinity, of 3 minus 1 over n cubed over 2 plus 1 over n cubed. And as we said, this one and this one go to 0, which leaves me with what? 3 over 2. So this limit converges. And it actually converges because I found a limiting value. If at the end of this thing this said infinity, which it will sometimes, then would it be converging or diverging? It'd be diverging. So the directions always feel a little bit funny to me because what you're actually doing is you're looking for the limit and then you're going back and saying if it converges or diverges, right? The directions always feel backwards because you're doing both those things but in a reverse order. All right, let's try another one. It looks a little bit different. This is kind of a rational expression one where you see a polynomial on top, polynomial on bottom. It's a very classic kind of an example. Another one here that you're going to see is ones that look like this. All right, so what does the exclamation point mean? It's factorial. Yeah, so factorials are also quite nice to look at in ratio form because things start canceling out. If you've taken statistics, permutations and combinations have lovely things that just reduce and cancel out. We often want to cancel before we actually multiply things because much of it goes away. Well, much of this is going to go away as well. So we'll just start this from the perspective of finding the limit. So what we're going to do is we're going to write out enough to see what exactly cancels. So just as a reminder, let's just, well, not as a reminder, but as a starting point, let's start with the denominator. How will I write, or could I write n factorial so that I see a few of the terms? All right. And could I write a few more out if I needed to, Hannah? Sure, I could. I could write more out. It's kind of nice to stop there, though. Why? Yeah. The top is exactly n minus 2 factorial. Now, you need to be a little bit careful with factorials, especially depending on your comfort level with them. Remember, you can't cancel things out within like the factorial notation. These cancel only because they're exactly identical, right? So like I couldn't over here do something like this. That would not be appropriate, yeah? No. So the only reason they cancel is because they both say n minus 2 factorial. So now what I have, let's just kind of reduce what I have left. No space over there. What do I have in the numerator? Just 1. And the denominator now I have n squared plus, I'm sorry, minus n. Now if you like, we could do the 1 over n squared. I mean, n squared's our largest, exponent, kind of like I did on the first problem. You could do that. I think it's a little bit overkill at this point. Take a look at what you have in the denominator. What happens as you have n squared minus n? What kind of numbers do you get if you plug in n equal 1, n equal 2, n equal 3, n equal 4? What's going to happen? It's going to increase, right? It's going to keep going larger and larger, agreed? That's going to go to infinity, infinitely large. If you think about a polynomial, if you think about the graph, just the n squared minus n, think about x squared minus x. What kind of a graph would that look like? It's a parabola, right? It's either a parabola opening up or down. Since n squared is positive, it would be opening up. And what happens on the ends of a parabola? They approach infinity, right? They get infinitely large. So this denominator, however it is you're thinking about it, is getting infinitely large. What's happening in the numerator? It stays the same. So what happens when you divide 1 by something that's getting infinitely large? It goes to 0. It goes to 0. So this limit is actually 0. Oh, and you know what? I said it on the last one. I didn't write it down. We do need to write that these converge, right? That's actually part of the question. It said, does it converge or diverge? So we'll write converge. Okay, so factorials is another nice example. All right, let's take a look at one more that's a very classic example of sequences. This one right here we're going to look at is, I hate the notation when this happens, but it's sine of n. I know it looks like I just put two n's beside each other. Try to give yourself a little space. Over n. And if you were in a trig class, we'd have to be careful to make sure to tell you, don't cancel the n's out. That's not appropriate, right? But we're not. And you guys know better than that. So let's kind of think about what's happening in these two particular parts of the equation, right? So the numerator is sine. What does sine do? Yeah, it oscillates, bounces up and down between 1 and -1. Fantastic. So it's sort of bounded, and it's this bounded curve, right? It's not approaching anything. It just keeps going up and down forever. But it does have it's contained, right? It doesn't go up to 2. It doesn't even go to 1.1, right? It's contained within a specific bound. What's going to happen in the denominator? It gets infinitely large. So our expectation is that what happens on this particular function? It goes to 0, right? I've got something that's bouncing back and forth between 1 and -1, and it's dividing by something getting infinitely large. Eventually it goes to 0. And remind me your name? Deborah was over here drawing kind of her expectation, and she's right to think so, is that it's kind of doing like this, right? All in all, this looks like it's going to be bouncing up and down, but getting less of a bounce as the time goes. That's our expectation of what this happens. But we need to do more than just expect that that's going to happen. We need to show how it's going to work. So what I'm actually going to show you is how we do that with a particular theorem. So we're going to talk about the squeeze theorem. Have you guys heard the squeeze theorem before? Whoops, that was not spelled right. Yeah? That's right now, isn't it? Okay, I think I got the spelling. Squeeze theorem. Do I have 2 E's in the middle? Am I supposed to have 2 E's in the middle?
Yes.
Yes? Man, it just looks terrible. Somebody tell me how to spell squeeze. Man, you guys. Okay, squeeze theorem says the following. If the limit as n goes to infinity of a sub n equals L equals the limit as n goes to infinity of b sub n. So you've got two sequences, they approach the same limit. Everybody good so far? Okay. And there exists a natural number n, not natural number, an integer n. It could be a natural number. That's probably overkill, but I just copied it from your book, so we'll go with it. Such that a sub n is less than or equal to c is less than or equal to b sub n for all n greater than n. That should say c sub n. It's missing my subscript. Then the limit as n goes to infinity of c sub n is also L. So let's think about this in terms of functions. I mean, sequences are discrete objects. That's just, they're dots if you were to graph them on a number line, you know, on a two-dimensional plane. But just think of them with the full graph as though it's a function, first of all. What this is describing is two functions, right? They're both approaching the same limiting value. So you might have in your mind something that looks like this. One function that's coming at it from above, another function that's coming at it from below. Doesn't have to be that way, but that's a pretty good idea to think about it. And at some point, there's another function, right? And it may do some weird stuff eventually, but at some point, it's trapped between the two. Okay, there's some far enough along in the sequence that c sub n is trapped between a(n) and bn. So this is saying then that if the a sub n and b sub n are going towards the limiting value of L, then so is c sub n. Make sense? Okay. Now, but in order to actually use the squeeze theorem, you would actually have to have two sequences, right? That are both approaching the same value. So let's actually see how we can use the squeeze theorem back on example 4. So here's our example 4. And we're going to take a look at what we know about sine. You guys told me a minute ago that sine is trapped. It's bounded between -1 and 1. So far, so good? Yeah, all good. Now, our n is a natural number. It's positive, right? We're not looking at negatives. So it's actually also true then that I could divide everything by n. And it would not change the direction of our inequalities. They would still be less than or equal to inequalities. Agreed? Okay. But we already talked about this. What's the limit of -1 over n as n goes to infinity? It's 0. What's the limit of 1 over n as n goes to infinity? It's 0. And where is sine? Squeezed in between, isn't it? So it has to be 0 as well. So let's actually write that down. What we have then is that the limit as n goes to infinity of -1 over n is less than or equal to the limit as n goes to infinity of sine of n over n, which is actually our question, right? Is less than or equal to the limit as n goes to infinity of 1 over n. This value is 0, and this value is 0, and the limit of n as n goes to infinity of sine of n over n is sandwiched in between, which means it's also 0. So this is the squeeze theorem, so thus by the squeeze theorem, the limit as n goes to infinity of sine of n over n is 0, and that means obviously that it also converges to 0. So at this point, maybe you're like, they've all converged. What would it look like if they didn't? That's my next example. So let's take a look. Let's try number 5. This a sub n is going to be another rational one. For n squared over n. So what could I do?
Divide by 1 divided by n for the greater denominator.
Okay, so limit as n goes to infinity. And what was your idea, Ethan?
Divide the greater denominator by n, 1 divided by n.
That'll work. You could use 1 divided by n squared as well. Either one will work fine. So you said 1 over n, so we'll use that one. That's actually the one I have written in my notes too, is to do it that way. So if I were to use this division factor of n, what am I going to be left with on top? For n plus 2 over n. And on bottom? 1. So let's look at what the pieces do. Obviously, the 1 in the denominator is a 1. It's not real helpful at this point, right? It doesn't do anything. It's just always 1. What happens to the 2 over n? That goes to 0. What happens to the 4n? That goes to infinity. This piece is infinity. So I have infinity plus 0. That would be infinity. Divided by 1, which would also be infinity. This one is actually infinity, which means it diverges. If you had chosen, just kind of to give you a heads up, I'll change colors. You don't need to write it down necessarily, but I want to show you. If you had chosen 1 over n squared here instead of n, you would have ended up here with 4. You would have ended up here still with something going to 0. I mean, that's not happening, or not a big deal, but you would end up dividing by something also going to 0. Right? And if something is divided by something going to 0, that means that the result ends up going to infinity, since it's constants on top, and then it would be going to 0 on bottom. So that's actually how you could handle with that too. All right, another one. What happens if we go with something like this? Natural logs. I mean, that's not a rational expression. I can't just multiply by something over something else. I don't have a sign value that's trapped between something. There's no factorials to deal with. What do you think? Hopitals Rule. That is exactly what we're going to do. So let's take a look at what Hopitals Rule says. I'm just going to go to another slide for that, and we'll come back and finish this. So L'Hopital, you even said it right. I can't tell you how many people look at this and tell me it's La Hospital. It is not La Hospital. It's Hopitals Rule. Hopitals Rule, you've seen it before. You dealt with it, I believe, chapter 8, Calc 2 in your book is where I think it falls. So, what's that? Basically the last chapter, yeah, which you may not have done in order. I know when I teach it, I don't do chapter 8 as my last chapter, but yeah, but it is. It's the chapter right before the one we're doing. Hopitals Rule, and I'm just going to give you an abbreviated version of it. Okay, so this is shorthand for sure. Says that the limit, as specifically for functions as x goes to c, of f of x over g of x is equal to the limit as x goes to c, or of f prime of x over g prime of x. That's what it said back in chapter 8, okay? And this applies to sequences too. Why? Because they're functions. So it applies to sequences. The other thing is that it also applies specifically when the x in this function notation goes to infinity. It actually was talking about it going to a specific value of c, x approaching c over here on the left. It actually applies when it's going to infinity as well, which we need that because our sequences are looking at limits that they go to infinity. So let's take a look at what happens back with Hopitals rule in our last example. If I'm taking a look at this one and I want the limit as n goes to infinity of the natural log of n cubed over 2n, I can do this with Hopitals rule. There's a couple of ways I can deal with logs. Maybe you remember log properties. If so, that's fantastic. If not, you can deal with the log derivative on top by using the chain rule, and that's also going to work just fine. It's not a terribly messy one. So would you guys like to remember log properties, or would you like to do the chain rule? Log properties? Yeah? Okay. One of the log properties, if you'll remember, is that when you have an exponent inside of the log, I'm talking about this 3 right here, that's the same thing as it being a coefficient. This is 3 times the natural log of n over n. Where'd my 2n go? Oh, 2n, thank you.
1 over n cubed times 3n squared.
Yep. Yeah, if you did the chain rule for natural log of n cubed, it would be 1 over n cubed times 3n squared. So it's not particularly messy on this one. Logs can get super messy, and log rules come into play really nicely to simplify. So far I have not actually used Hopitals rule, right, with what's on the screen. But if I were to try to talk about this as what happens, the natural log of something that gets infinitely large is infinitely large as well. Not as fast, but it also continues going upwards. Log graphs continue increasing forever. And clearly the 2 times n in the denominator also increases forever. That's just a line with slope of 2. So these are both, like this is infinity over infinity, right? And that's only the time infinity over infinity or 0 over 0, that's when you get to apply Hopitals rule. Okay, you don't just apply it in general. It has to be those conditions. So you have to check and make sure you can actually apply it before you go, doing that. And sure enough, I'm going to write this in just as a reference point for me. That's why I'm going to do it in red. This really is infinity over infinity currently. These individual limits are infinity. So if we use Hopitals rule and take derivatives, what do we get? What's the derivative of 3 times the natural log of n? It is 3 over n. What's the derivative of 2n? 2. Okay. So I actually have a constant in the denominator now, so I wouldn't be needing Hopitals rule again by any chance because there's no infinities left, right? At least not on one part of it. What happens now in the numerator if I put in infinity? 3 over infinity. What is that? That's 0. So this piece goes to 0. The denominator is 2. So what is the whole thing going to give me for the limit? It's 0. And this converges then.
Quick question.
Yep.
We use the Hopitals rule.
L'Hopital.
L'Hopital.
Yeah.
Hopitals rule when it's infinity over infinity, 0 over 0.
Yes. Infinity over infinity, 0 over 0. If it's not one of those two, it doesn't apply. All right. Shifting gears slightly, we're going to introduce one more definition. Actually, there's 2 more. We'll probably have time for both of them. A sequence A sub n is monotone. That doesn't mean boring. Monotone, actually I've got the word monotonic written down. We'll go with monotonic. When its terms are non-decreasing So non-decreasing means a sub 1 is less than or equal to a sub 2 is less than or equal to a sub 3. The reason it doesn't just say increasing is you could have some of them that actually are identical. So we're looking at increasing or constant. That's what that's describing. Non-decreasing means increasing or constant or some combination of those things happening. So if it's when its terms are non-decreasing or non-increasing. So non-increasing would be the reverse of what I just wrote down. So a sub 1 would be greater than or equal to a sub 2, and a sub 3, and so on. Okay. So we're not talking about like the sine function where it's bouncing up and down. That's not what we're doing, right? We're looking at basically things that are either increasing or decreasing or constant, okay? Just one more definition for us along these lines. A sequence is bounded above when there is a real number m such that a sub n is less than or equal to that m for all n. I kind of hope you're picturing something that looks like an asymptote. That's the image. A horizontal asymptote, right? It bounds it. That's what we were picturing here. We call m an upper bound. So m is an upper bound of a sub n. If I can define it that way for an upper bound, there's a similar definition for a lower bound, okay? So similarly, if a sub n is greater than or equal to n, we're going to use capital N here, then n is a lower bound of a sub n. And a sequence is bounded. I've actually already used this phrase today when we talked about sine, is bounded when it's bounded above and below. All right, I'm going to write out our question of our example. I'm not sure we have time to actually do it, but we'll be ready to go with it next time. It's the last thing that I have for you in this lesson as well. So we're going to determine.
Can you go back to the last page?
Oh, I'm so sorry. You bet.
Sequence is bounded when it's bounded.
Mm-hmm.
Thank you.
You bet.
So that would be like a sine.
Yes, sine function would be a bounded function, you bet. Determine whether the sequence, notice sine would be a bounded function, but it wouldn't be monotonic. Those are two separate descriptions. Determine whether the sequence is monotonic and or bounded. and we're going to confirm with the calculator. So we're going to confirm graphically. Here's our sequence. A sub n is equal to n minus 1 over n plus 1. So I don't have time for us to take a look at doing this particular problem, but grab your calculator real quick. I have a feeling you probably know, roughly speaking, what this graph looks like. It's a rational function. Have to remember that n is only greater than 1, right? 1 or bigger, because that's how we're doing, I mean, that's what sequences domains are. So you're only looking from 1 to infinity on your graph. Visually speaking, is it monotonic from 1 to infinity? Don't look at the left-hand side. Does it look like it is? Okay. Monotonic means it's only increasing or only decreasing. And does it seem to be bounded? Does there seem to be a place by which we don't go above, a place by which we don't go below? Is it leveling off from above or below? I don't have my graph drawn. Does it decrease or increase? It increases? Okay. So if it increases, and wherever it starts could be the down below, wouldn't you agree? Yeah, it's not approaching that, not asymptotic, right? But the bound above would be asymptotic. All right? I'm going to go ahead and write down the homework. It's not assigned, it's not due next time, but if you would like to go ahead and start it, I know some of you have been asking, you'll already have it, and you can start looking at it. It's page 592. Numbers 4, 21, 24, 30, 36, 37, 41, 44, 54, and 57. So since we're not quite finished with this example, we'll finish it next time. This homework won't be due until Friday, and I will also adjust the web assigns so that it won't be due until Friday. Okay? Have a great week, guys.